In this session, we're going to be looking at lessons 26, 27, and 28. In lesson 26, we're going to introduce the concept of logarithms. And logarithm is just a fancy term for exponent. That's all that means. And so logarithm, it's a different way to deal with exponents and to solve for exponents. Two forms of equations for log equations. You have exponential form, which is what you are used to, where you have something like 3 to the y equals 4. So this would be your equation right here. 3 to the y equals 4. Now, the base is 3 here. That is the base. Y is the logarithm or the exponent, which you've always known the y is the exponent. And 4 is the anti-log, or I call it the answer. Now, another way to write this is log 3, 4 equals y. Whereas the base is still 3, the logarithm is still y, and the anti-log is still 4. It's just rearranged in a different form of an equation. So another one, they're going to give you an example like this. They're going to say log x4 equals m. And they want you to write that. Obviously, this is log form. And they want you to write it in exponential form. How do we do that? Well, you just take the labeling of log form and change it to the labeling of the exponential form. So it's x is the base, m is the exponent, and 4 is the answer. So this would be writing this particular problem in exponential form. All right, let's look at some examples and actually solve for some things. Here are 3 examples where you have something missing in a different place. This first example, we have the base is missing because it says log b 9 equals negative 1/2. Right here, the exponent is missing. Right here, the anti-log is missing. Well, the easiest way to solve these by hand is to rearrange these into exponential form. So it's b to the negative 1/2 equals 9. B to the negative 1/2 equals 9. Well, what to the negative 1/2 equals 9? Well, the way that you're going to write this, is just like solving for anything. You're going to multiply both sides by negative 2. When you do that, this will cancel. It's just like all of algebra. You're solving for the variable. So 9 to the negative 2 is 1 over 81. Look at the next one here. You have 3 to the m equals 1 over 27 when you rewrite that. And so 3 to the what is 1 over 27. It's going to be, m is going to equal 1/3 because 3 cubed is 27. Actually said that wrong. It is, it's negative 3, not 1/3. Same kind of thinking the wrong way to do it, but it's to the negative 3 power because 3 cubed is 27. Negative 3 brings it to the bottom and you get 1 over 27. Last one here, you get 1/3 to the negative 2 equals p. This one you can literally put in your calculator to come up with the answer. And the answer here is going to be 9. As you bring the 3 to the top, it becomes 3 squared. 3 squared is 9. Lesson 27 you already know how to do because I taught you how to do the trig functions in the calculator, so it kind of skipped you forward a little bit. We can look at those in class if you struggle with it, but you just put it in your calculator and you look at the chart to see what the numbers come out to be. On lesson 28, we have factorial notation here, and you're going to put these in your calculator. 9 factorial divided by 3 factorial times 5 factorial equals 504. These are not difficult problems either. You use the factorial button in your calculator. Make sure to use parentheses like you need it in order to come up with the right answer. We can look at those in class if you struggle with those, but that is not a difficult problem for you. You just have to find the factorial button on your, it looks like an exclamation mark. You find on your calculator. The last thing we're going to look at on lesson 28 is abstract rate problems. Remember that, abstract distance problems, rate problems. Remember that rate times time equals distance. So we're going to take this concept in order to solve for these. And what they're going to do is they're going to give us kind of a case 1, case 2 scenario. So in this case 1, it says that the train traveled m miles at p miles per hour. So the time we do not know. So it goes at p miles per hour in place of the rate. The time we don't know, and the distance was m miles. So the time it ends up being m divided by p. So the time is m over p. And it actually says they still arrived 1 hour late. So how fast should the train have traveled to travel on time? So they say that it is 1 hour late. And so rate times time equals distance. Let's go in our case 2. Here's case 1. Let's go case 2. We're going to take this time, and the new time is going to be 1 hour less. The distance is going to be the same. And it's the new rate, because they say how fast did they need to go in order to be there on time. And so we could put this in a little, instead of m over p minus 1, it could be m minus p over p to get common denominators there. So we're going to flip this and bring it to the other side. And when you flip and bring it to the other side, it ends up being mp over m minus p. And this actually is the new rate that it needs to be in order to get there on time. Once again, you're going to look at this and you're going to think, this is, it's just letters. And that's what the word abstract means. So that's how you solve for these types of problems. Which, by the way, this should have, because it was a rate, needed to be miles per hour. Make sure to label that. I'm going to show you one more example to make sure that you guys have the hang of this. Let's look at this next example. It says the boat traveled k miles in t hours and was 40 miles short of the goal when the gun went off. If the skipper tried again, how long would it take to reach the goal if she increased the rate of travel by 10 miles per hour? Okay, look at the first set. The first thing is they don't give us the rate, but they do give us the time is t hours and the distance is k miles. So the rate is k over t miles per hour. So this is our first case rate. Then it says that they were 40 miles short. So they were 40 miles short when the gun went off. Then it says the skipper tried again, if he attempted this again. How long would it take to reach the goal if she increased the rate of travel by 10 miles per hour? So if this is the rate, the new rate would be plus 10 miles per hour. So this would be our new rate. And the question is, how long would it take? So we're looking for the new time and the new distance. We were 40 miles short, so the new distance is going to be what we had plus 40. They want to know how long would this take. Once again, I think it would be good to go ahead and put k plus 10t on top all over t. And really, all you're going to do is flip this and bring it to the other side. So you're going to have k plus 40 times t all over k plus 10t. And this is the new time. So this is going to be hours. This is an abstract time. And that is it for lessons 26, 27, and 28.